Welcome back. So in the last lecture we have seen our first discussion on the types of vehicles, then we have gone into our types of converters which will be used in the charger and on the vehicle. Then we have started with our discussion on the power electronics converter, where we have seen what are the components which will be present. We have discussed about the operation of inductor, capacitor, then we have gone into diode and MOSFET, where diode is your uncontrolled device. Whenever we apply and positive bias through it, it carries the current. When we reverse bias it, it gives us infinite resistance. Then we have seen the MOSFET. So MOSFET falls in the family of fully controlled device, where we have 3 terminals, 2 power terminals and 1 gate signal terminal. So when the signal is present, the MOSFET will be conducting. When we remove the gate signal, it will be turning off. And the MOSFET characteristics are, it will be having lower switching losses and it is having higher conduction loss. So it is used in applications where we will be having higher switching frequency and low current or low power circuits. Okay. So then we had BGT, which had the complementary characteristics, that it had low conduction loss, but it could not operate at an higher switching speed. Whereas the MOSFET characteristics was, it was having faster speed of operation, but it had larger conduction loss. So there was a thought process of combining the best features of these two devices, and the IGBT was developed. So in IGBTs, what are the properties it offers? IGBTs are faster than the BJT when switching performance is compared. When we compare the losses, so it will be having less loss compared to the MOSFET. So it combines the benefits of MOSFET and BJT, and its performance lies in between both of them. So it is easy to drive because it will be not requiring any gate current, it will be insulated. We will see that in the next slide. So IGBTs, so it will be used in complementary applications where the switching frequency will not be that high, but the current will be higher or the power rating of the converter will be higher. So there we will be going for IGBT. So the operation of IGBT also similar. So it has two power terminals, collector and emitter. So the current will be flowing through this whenever there is a gate signal. When we remove the gate signal, your current flow will be stopped or it will offer very high resistance. Then these are the some of the IGBTs which are available in the commercial market. So this is similar to an transistor with an insulated gate. In the transistors, we required a higher amount of base current. That limitation has been addressed. So its gate is insulated, so its gate power requirement will be very less. It allows dV by dt and di by dt control by the gate signal. So appropriately adjusting the gate signal, we can adjust these parameters. It has lower on-state drop compared to your MOSFET, and it has higher turn on losses. So its switching performance is not as good as the MOSFET, but it will be having lower conduction loss. So it is used in the applications where we will be having high current through the circuit or high power circuits, and the switching frequency will not that much high. So there we will be going for here IGBTs. So low gate power requirement, as it is insulated, so it will not require much power to turn on the circuit. Then the structural wise, how it is different from your MOSFET. So if you see, we have an additional layer of P plus, remaining the structure is the same as that of your MOSFET. So what is the advantage of having this P plus? It brings us the blend of your MOSFET and the BJT characteristics together. And whenever this circuit, if you see, there is an equivalent thyristor circuit inside it. So we do not want this parasitic thyristor to be turning on. Okay. So this is the simplified geometry. So in the real applications, we will be having slight variation in this geometry, which is shown over here. It is just for our understanding. So here, if you see the n plus layer which is present over here, the n plus layer over here, this is an optional layer. Okay. So if we do not want this layer to be present, we will be having one type of IGBT. If this layer is present, we will have the other type of IGBT, which is listed over here. N plus buffer layer, if that layer is present, it is called as your punch through IGBT. If this layer is missing, it is called as non punch through IGBT. So what is the benefit and limitation of these two solutions? So if we have this N plus buffer layer, so what will happen in this, due to this N plus buffer layer, your blocking voltage of IGBT will be reducing. That is, when we are applying a negative voltage across the IGBT, it cannot block that much amount of voltage which it can block in the forward direction. Okay. So it is called as asymmetrical IGBT or punch through IGBT, where we will have this N plus buffer. As N plus is written, so the concentration of the higher will be higher. So P plus is having high concentration and N plus is having high concentration. When we have high concentration of doping material, the blocking voltage or the blocking capacity of the junction decreases. Because of this, this will not be able to block your reverse voltage. So that we say that as asymmetrical IGBT, because its reverse blocking voltage will be less compared to your forward blocking voltage. The other solution is where we remove this N plus layer and we will only have P plus followed by the N minus layer. Okay, so that solution is called as non-punch through IGBT. So what will be the limitation of this non-punch through IGBT? This non-punch through IGBT, as I said, it will be addressing the limitation of your punch through IGBT. That is, it will have symmetrical voltage blocking capacity, that is the positive voltage and negative voltage blocking capacity will be the same, but as we have an N minus layer adjacent to P plus layer, its switching speed will be somewhat less compared to the punch through solution. Okay. So, based on our requirement, we can select any one of these, and the doping of this N plus layer also can be adjusted to adjust the switching performance. Now, these are the some of the examples of commercially available IGBTs. Their data are given over here. Till now, what we have discussed, we have seen our basic elements which are required to construct a converter. Any converter, may it be AC to DC or DC to DC converter, which will be used on the vehicle as well as on the charger side. Now, we are starting with our discussion on the onboard converters, which will be present on the board of the vehicle, or it will be moving along with the electric vehicle. So, first converter which we will be seeing is our DC to DC converter. Okay. So, in this DC to DC converter, there are two different types, that is your isolated and non-isolated. Okay. So, what is an isolated DC to DC converter? So, in this isolated DC to DC converter, there will be no continuous electrical path between the source and the load, whereas in the non-isolated, there will be continuous electrical path from the source to the load. So, what are the types of non-isolated DC-DC converter? The basic one is your buck converter, then followed by your boost, then buck and boost. Then we have some fourth order DC to DC converter also, which we will not be covering over here. So, this fourth order are addressing the limitations of these three basic second order DC to DC converters. What is second order and those things, we will see that in next few slides. So, the isolated DC-DC converter, here we will be having an isolation in between the electrical path, or there will be a discontinuity in the electrical path. So, the best example of providing the isolation is a transformer. We will see how the transformer can be used in a DC to DC circuit when we go into these converters. So, the best example will be flyback forward, and we will see a brief discussion on the dual active bridge converter. Okay. So, now let us first understand why we require DC to DC converter, as the input is also DC and the output is also DC. So, there is no conversion of voltage. So, why we require a DC to DC converter? When we will have mismatch between your load and your source voltage. Suppose in this case, here we have a source of 100 volt with us, but our load is requiring 60 volts. So, how we can match the profile of the source with the load? So, when we have this type of variations, we will be requiring a converter in between, which is a DC to DC converter, as the input as well as the output is DC. So, we will just shift the voltage levels as per the requirement of the source and the load. So, in our electric vehicle application, so why we require this DC to DC converter? As we have discussed in the last lecture, the battery voltage will be variable, it depends on the SOC. So, we will have a difference of the terminal voltage based on the state of charge on the battery, but on the load side, when we are driving at a constant speed, we will be requiring a constant power to be fed to the motor, or the DC link voltage has to be constant. So, there will be a converter in between which will maintain this task irrespective of the terminal voltage of the battery. The DC bus voltage will be maintained constant by using a DC to DC converter. Okay. The simplest example of this converter is buck converter. In the next few slides, we will see how your buck converter was designed. Okay. So, first let us take a simple switch which will be connected between the source and the load, and we will be operating it with a duty ratio of 60%. Okay. So, why 60%? Because our input voltage is 100 and output voltage requirement is 60. So, I will be turning on for 60% of the time and I will be turning it off for the rest of the cycle. So, the average voltage will be 60 volt as per my requirement, but what limitation it has? So, we have turned on the switch for 60% of the time during when the switch is on, neglecting the on state of the device. So, your load will be subjected to 100 volts, but it was designed to handle a maximum of 60 volts. That is what was the rating of our load. So, it will be subjected to high voltage, which can cause damage to our load circuit. So, this solution, how it can be addressed? We can connect an capacitor at the output stage, which will maintain the voltage at 60 volts. Okay. Now, if I close the circuit, so what will happen now? As I wanted to minimize my voltage ripple, here when the switch was off it was 0, when the switch was on it was 100, but I wanted a constant voltage of 60. So, I have connected a capacitor to filter out the voltage ripple. Okay. But will this solution work with us? No. When the switch is closed, what will happen? Now, this capacitor was having 60 volts suppose, and it was discharged during the off time of the switch, because it will be feeding the power to the load through this path, and it will be discharging. Okay. So, the energy stored inside the capacitor will be half CV square. So, as the source is disconnected, it will be feeding the stored energy into the load and maintaining the current. Okay. Now, as soon as I close this switch, suppose it had discharged a slight below 60 volt, suppose 59 or 58 volts. Now, we have closed the switch. What will happen? Suddenly, we are connecting two voltage sources of different voltage. It is at 100 and our capacitor is at 58 volt. Suppose then the switch will be subjected to an huge inrush of current and the switch may be damaged. So, what component has to be added? Now, we can think of inductor, because inductor does not allow sudden change in the current. So, we can put an inductor in the path. So, when my switch closes, now the inductor will not allow sudden rise in the current, it will limit the current. But the main issue with this solution will be when the switch will be disconnected, my inductor had some finite current flowing through it. We have seen the behavior of our inductor, it will never allow sudden change in the current value. So, the moment I try to disconnect this, it will see that the current is suddenly changing, it will induce an high amount of voltage which can damage the switch. So, what can be the next solution? So, the next solution is, instead of breaking the path of inductor, we will provide an closed loop path. Okay. So, how to provide a closed path? Best solution is to connect an freewheeling diode. Okay. So, why it is freewheeling diode? It just allows the current to circulate through it. Okay. So, now when I close the switch, the inductor will be charging and it will be limiting the current which will be flowing into the capacitor. It will not allow sudden rise in the current. Then when the switch is disconnected, my inductor current was there, so it will be flowing through the diode. Okay. So, this is the basic DC to DC converter which we have discussed now, that is called as your buck converter or an step down converter. Why it is called a step down converter? We will see that when we see the input output voltage relation. What are the application of this basic step down DC to DC converter? It is used in our laptops, auxiliary EV power supplies, LED drivers, communication circuits, power supplies. Okay. So, what is auxiliary EV loads? So, in this we have the task of driving the motor, that is the primary task of the battery source which is present. So, we will have one add-on function also required with this primary task, that is to make some auxiliary supplies. What are those auxiliary supplies? The best example is your automatic door closure, the audio video system which is present inside the vehicle. Those things will be fed from the auxiliary unit. Okay. So, there will be an small low power tapping from the battery bank which will be providing the power required to the auxiliary circuits. Okay. For this type of applications we can use an buck converter. Now, let us discuss the operation or try to find out what is the relation between the input and output voltage for this buck converter. Okay. So, for before going into the analysis, we will take some assumptions. What will be those assumptions? First is the circuit is operated in the steady state. Okay. So, what is a steady state, or how to define the steady state of an DC to DC converter? Now, in this case, average inductor voltage is 0. First way to identify is, if my average inductor voltage is 0 over a cycle. Okay. So, what is a cycle? The 1 by switching frequency or the speed at which I will be operating the device, that is one turn on and turn off time of my switch will be denoting one switching cycle. Okay. So, now if I integrate the inductor voltage over a switching cycle, if it is giving me 0, then we say that circuit to be in steady state. Okay. So, what is the logic behind this? Okay. So, if what is the meaning average voltage across the inductor being 0, that is the 0 change in current. So, the inductor current will be starting from the same point at the start of every cycle. Then we say that average voltage across the inductor is 0 and the circuit is in steady state. What is the other way around? The complementary device which is present with us from the capacitor, the average current across the capacitor should be 0. Why? If there is a net current flowing into the capacitor, suppose, so that we are charging the capacitor. If current is flowing into the capacitor, it will increase the charge storage, or indirectly it will increase the half CV square value or the energy stored across it. So, your voltage will be changing. If I want it to be remaining constant, so average current through the capacitor should be 0. So, if I integrate the capacitor current, instantaneous capacitor current over a switching cycle, if it gives me 0, then I can say that the DC to DC converter is operating in steady state. Okay. Then power supplied by the source is same as that delivered to the load, that is we are not considering any amount of losses in the circuit. If we neglect the losses in the circuit, whichever power is drawn from the source, that will be given to the load. Okay. Now, what are the other assumptions? First is inductor current is continuous. Okay. So, what is the meaning of inductor current being continuous? Okay. So, we will have when we go ahead with this lecture, we will see that we will have two different modes of operations for this converter. When this inductor current is continuous, that is it is either positive or non-zero. Okay. So, it will always be non-zero value. If it is 0 for finite time, then we say that the current is discontinuous. Okay. So, these are unidirectional device, that is unidirectional converter, that is the current will be flowing from the input side to the output side. The vice versa power flow is not possible. So, it is an unidirectional DC-DC converter. So, it cannot have negative inductor current. So, it can either be positive or 0. Okay. So, if it is positive for the entire cycle, we say that the current is continuous or the converter is operating in continuous conduction mode. Okay. So, it is based on the inductor current how we decide the mode of operation for this converter. If the inductor current is continuous, we say continuous conduction mode. If the inductor current is 0 for an finite duration over a switching cycle, then we say that the inductor current is discontinuous and this DC to DC converter is operated in discontinuous conduction mode. Okay. The first we will see with the continuous conduction mode of operation. Next, the capacitor is very large. So, when we are discussing or calculating the parameters of an inductor, we will assume that the output voltage is constant because of a large capacitor over here. Okay. So, this is done just for our simplicity in the analysis. Okay. The components are considered to be ideal. So, what is the meaning of that? We are considering the inductor to be ideal inductor, capacitor to be ideal capacitor, and the onset drop of the devices to be 0, switching loss of the devices to be 0. So, these are all the assumptions which we have taken. So, why we are considering the circuit to be ideal? So, as to simplify our analysis. Okay. Then we are not considering, as I said, we are not considering any switching loss. So, that means the switching time is also not considered. So, what is the meaning of that? The moment we close or provide the gate signal to the switch, we assume that the switch has been closed. The moment we remove the gate pulse from the switch, we assume that it has opened. Okay. So, the switch will be on for dt amount of time, where d is the duty ratio or the fraction of time over a switching period for which the switch is in the off state, and complementary time, your switch will be off state, that is 1 minus d, the switch is assumed to be open. Okay. So, this statement is true when we neglect the switching time. Okay. So, every device will have some finite switching time. So, what is the meaning of finite switching time? There will be a small gap between activation of your gate signal and the actual turn on of the switch, and similarly there will be a slight delay after removal of the pulse and the time taken by the device to go into the blocking state. Okay. So, that delay we are neglecting and we are assuming the device to be ideal. So, it is turning on for dt amount of time and it is turning off for 1 minus dt amount of time. Okay. So, now let us consider the switch is closed and try to see what will be the various voltage and current equations. Okay. So, as the switch is closed, now what will happen to this diode? Okay. So, if we see, this is the N terminal of the diode as we have discussed. So, now this N terminal is connected to the positive terminal of the supply. So, your diode is reverse bias. So, it will not be able to carry any current. So, it will behave like an open circuit and we assume it to be infinite. Okay. So, now this will be the equivalent circuit. A diode cannot conduct when the switch is on. So, the inductor will be connected in the path and it will be seeing the capacitor and the load parallel combination connected to this node. Okay. So, now if I assume the input voltage as Vs, voltage across the inductor as VL and output voltage at V naught, which will be equal to the capacitor voltage, because both of them are in parallel. Okay. The capacitor voltage as well as your output voltage can be said as V0. Okay. Now, what will be the voltage across the inductor? The difference between the two voltage, because the diode is not in the conduction path. Now, the inductor will be seeing an voltage which will be equal to the difference between the source and the load voltage. Okay. So, now we know that when there is an finite voltage applied across the inductor, it will experience L di by dt, that will be equal to Vs minus V naught. Okay. So, now rearranging. So, di by dt will be given by Vs minus V naught by L. Now, with an assumption that my switching frequency is very high or the dt time will be very small. So, I linearize that and I consider small change in current by small change in time equal to Vs minus V0 by L. Okay. So, now if I what will be the delta t time or time duration for which the inductor will be experiencing this voltage, the time duration for which the switch is on. Okay. So, that is delta L by dt equal to Vs minus V naught by L. Okay. So, if I try to find out delta IL when the switch was closed or the change in inductor current when the switch was in closed state, that will be equal to Vs minus V by L into dt. Now, the next stage, after my dt time has finished, now I will remove the gate signal from the switch. Okay. The moment I remove the gate signal, we will assume that the switch has gone into blocking state. Now, as inductor was having finite IL current flowing through it, it will try to maintain that current. So, how it will maintain? So, it will make this freewheeling diode come into conduction path, because the current was flowing in this way when the switch was on. So, it will try to maintain that current. The diode can carry current in the arrow direction. So, yes, so diode will get forward bias and your inductor will close the path. Okay. So, now your inductor in this case will behave as a source of energy. How it will behave as a source of energy? Previously, when the current was flowing through it, it will store the energy in form of magnetic field. Now, that field will be used to drive this circuit when the switch is open. Okay. So, this will be the equivalent circuit when my switch is in the open condition or when it is turned off. Okay. So, now what will be the voltage across the inductor? Now, if it has to maintain the current through this path, it has to minimum produce the voltage which is equal to the output voltage. Okay. So, if I apply KVL in this loop, I will see that VL will be equal to minus of V naught. So, now L di by dt will be equal to minus V naught. So, obviously your inductor is behaving as a source, so it will get discharged. So, that is what is the significance of this negative sign. So, now di by dt will be equal to minus V naught by L. Now, with the same line of assumption that our switching frequency is very high. So, we will replace the di by dt by delta IL by delta t. Okay. So, that will be equal to V naught by L. Okay. So, if you see delta I by 1 minus d into t, that is the turn of time, is nothing but delta t is nothing but in this case it is equal to 1 minus d into t. So, that will be giving me minus V naught by L. Okay. So, the change in inductor current when the switch is open is given by minus V naught by L 1 minus d into t. Now, coming back to our first assumption that we have made, that the circuit was in steady state. So, the inductor current should start from the same point over a cycle. And the second case, or how to derive the relation between input output voltage, we can calculate the average inductor voltage, it should also be equal to 0. Okay. So, from the first assumption, that is inductor current should start from the same point and end at the same point. So, for that case, delta IL closed plus delta IL open should be equal to 0, such that it starts from the same point at the beginning of every cycle. Okay. So, now from the above equations, if I replace them and I solve it, I will find out that V naught will be equal to d into Vs. Okay. So, now this is the relation between our input and output voltage. So, output voltage is given as the product of duty ratio and the input voltage. Okay. So, what can be the value of our duty ratio? The switch can be turned on from 0 to 100% of the time over a cycle. So, the duty ratio can be between 0 to 1. Okay. So, if I assume any value between 0 and 1, what will be the meaning of the output voltage, or what will be the value of output voltage? It will always be less than Vs. So, that is why we have called this converter, buck converter, as step down converter, because the output voltage will always be less than the input voltage. Okay. So, now coming to the various graphs of voltage and currents. So, the inductor voltage. Okay. So, first, what will be the inductor voltage? When the switch was on state, in the on condition, it was equal to input voltage minus your output voltage. So, Vs minus V naught. When the switch was in the off condition, it will be equal to minus V naught. Okay. So, that will be true for after dt time till the end of your cycle. Okay. So, from the second assumption, or the second way of finding out the relation between our input and output voltage, that is average voltage across the inductor should be 0 for the circuit to be in steady state. So, we will integrate the inductor voltage over a cycle, and we will find out that it will be giving us the same relation, that is output voltage will be equal to duty ratio time of Vs. Okay. So, from any analysis, that is average voltage across the inductor should be 0, or the current should start from the same point at the beginning of every cycle. These two cases can be used to find out the relation between our input and output voltage. Okay. Now, the relation between your input and output current. Okay. So, as already discussed, we will not consider the losses in the circuit, or we will neglect them. So, input power, or the power drawn from the source, will be equal to the power fed to the load. Okay. So, now VSIS, where VSIS are the input voltage and current respectively, will be equal to V0 I0, that is the output power by product of output voltage and output current. So, when VSIS, we are solving that, we know the relation between V naught and the Vs, it will be equal to duty ratio time of Vs. So, I have just replaced that, then the Vs will be cancelling out, will be left out with the relation between your input and output current. So, your source current will be equal to duty ratio time of I naught. Okay. So, if I find the output current, it will be equal to source current by duty ratio, as the duty ratio is always between 0 to 1. So, the current value will be higher than the input current value. The load current will always be higher than the input current. So, we can say that to be a current boost circuit, because it is increasing the current value. So, it is boosting it up. So, buck converter is a voltage step down circuit, or I can say current boosting circuit. Okay. Now, design of your minimum inductance value required to maintain the continuous conduction mode. As already we have discussed that we can have two modes of operation for this converter, where the inductor current will be continuous, or the inductor current can be discontinuous. We were discussing the continuous conduction mode. So, up to how much this continuous conduction mode will be valid, till and until our inductor current is continuous. Okay. So, at the boundary between your continuous conduction mode and discontinuous conduction mode, what will be that boundary? When this I min just touches 0 at the start of every cycle, or at the end of every cycle. Okay. So, if it just touches 0 and it becomes positive, then we say the converter is operating at the boundary of continuous conduction mode and discontinuous conduction mode. Okay. So, if I want to maintain the continuous conduction mode, I will be requiring a minimum inductance. Okay. So, if I am not using the inductor value greater than this minimum inductance value, I will not be able to operate the given DC converter in the continuous conduction mode. Okay. So, now let us find out what will be my minimum inductance required for this circuit to operate in continuous conduction mode. So, we will set this I minimum value to 0 to find out this boundary condition. So, what is I minimum? The average inductor current minus of 50% of the variation in the inductor current. Delta IL by 2 is nothing but 50% of my inductor current variation. Okay. So, here if you see, this is the average value. So, 50% delta, this peak to peak variation is delta IL as marked in this graph. So, 50% of that will be giving me the minimum value, average value minus 50% of the peak to peak ripple. Then that will be equal to average inductor current. What will be the average inductor current? It will be equal to V naught by R. Okay. Why it will be V naught by R? If you see in this graph, the current, average inductor current, will be equal to average output current. When it can be true? When this average IC is 0. Okay. So, as we are considering the circuit to be operated in the steady state mode, so IC value over a cycle is 0. So, whichever is the average current of inductor current, that will be same as that of your load current. Okay. If I apply KCL at this node, to the average values, I see that 0 amount of current is leaving through this path. So, whichever is the average current coming to into the node, that will be flowing towards the load. So, your average inductor current will be equal to the average load current, that is V naught by R. Okay. So, now I minimum is given by this. Now, we will be replacing that and equating it to 0. Okay. So, here what will be delta IL by 2? We have found out delta IL value in the last few slides. Okay. So, any state, that is, we have found out the variation in inductor current when the switch was on, and as well as we have determined the delta IL value when the switch was off. So, we can use any one of this. Here we have used the off state delta IL value. Okay. So, now if you see V naught by R minus of half into V naught by L into T is equal to 0. Okay. So, this is my value of inductor minimum current in terms of my voltages. Okay. So, if you see L minimum will be, if I solve this equation, I will find out that L minimum will be given by 1 minus D into R by 2F. Okay. So, similarly on the similar lines, if we try to design the capacitor for this buck converter circuit. Okay. So, now how the capacitor size will be determined? So, it will be determined to limit the voltage variation between an given percentage, 5%, 10% as per my requirement. Okay. So, now how this delta V will be controlled? By controlling this delta Q. Okay. So, we know that Q equal to CV for any capacitor. Okay. So, the amount of charge, if I replace this Q by delta Q, C can be replaced by delta V naught. Okay. So, the delta V naught is my performance parameter. It will be specified by the customer, that is 5%, 10% ripple is required. So, from that I can find out what will be the allowable delta Q value, such that the capacitor value can be calculated. Okay. So, now what is delta Q from this graph? Okay. So, if you see, this graph is formed by two straight lines. Okay. So, when we have an graph which is bounded by two straight lines, always it will bisect the x axis or the time axis in two equal halves. Okay. So, the time duration from this time to this time will be equal to the switching time period, 50% of the switching time period. Similarly, from here to here it will be 50% of the switching time period. Okay. So, we can consider any one of the areas. Okay. So, we will be considering the positive area which is shown over here as delta Q. So, in this, what will be the area of this curve? The area under your current and time axis curve will be giving us the charge. Okay. So, what will be delta Q value? It will be half into T by 2 into delta IL by 2. Okay. So, now if now delta V is equal to delta Q by C, now we have found out the value of delta Q. So, now if I replace this, this will be given as the equation for delta V naught. If I have the given capacitor size, so I can calculate what will be the percentage at the output ripple, and vice versa. If I know the delta V naught value, I can calculate the capacitor required for my circuit. Okay. So, now we will replace this delta IL by the calculated expression from our previous slides. So, this will be the final expression for delta V naught, which can be used for calculating the capacitor size, or if you are given with the delta V naught, we will be able to calculate the capacitor size. If capacitor size is known to us, we can find out what will be the voltage variation across the capacitor. Then the simplified expression over it, if generally the switching frequency of the circuit will be specified, so I can replace this switching time as 1 by switching frequency. So, that is how we have got this expression. Okay. So, this delta V naught by V, what is the significance of this one? Directly, if I am given with the percentage 5%, 10%, I can just replace it with this fraction. Okay. So, for convenience, we have simplified with this form. Okay. Now, the second mode of operation of your buck converter. So, the second mode of operation is your discontinuous conduction mode. We will see that in the next lecture. Okay. So, in today's lecture, what we have covered? We have seen our switching device, that was our IGBT, and we have seen that IGBT and MOSFETs has exactly complementary characteristics with each other. MOSFETs will be highly suitable for applications where we have high switching frequency and low power rated circuits, whereas IGBTs will be suitable for low switching frequency and high power circuits where the current will be higher, because it has low conduction loss compared to the MOSFET. So, IGBT will be preferred where the conduction loss is important for us, and MOSFETs will be preferred when the switching loss is important for us. Then we have seen the basic DC to DC converter, that was our buck converter circuit. in continuous conduction mode. We will continue from this in the next lecture to see the discontinuous conduction mode of the buck converter. Thank you.